Hi, welcome back students. Now we're in part 3 of CE Capillary Electrophoresis under instrumentation. Now there are two parts to this lecture. The first part is sample introduction and the second part will be detection. So first part we'll go through simple introduction where there are three main kinds of injection, where the most prominent ones are the electromigration injection and the hydrostatic injection. The last one is less common, so pneumatic injection. Back to CE principles of separation, we know that only a small amount of samples needed. That's one of the merits of CE. But the thing is, when we have small amount of the sample, how can we accurately inject this sample and withdraw it, and not to allow any gaps, right, of dead volume? And how can we measure using such a minute sample with a high sensitivity? So here we will illustrate more. The first thing is, remember you have a capillary that I showed you in class, right? It's very narrow, right? What you cannot see is, right, inside the internal diameter you can vary from 10 micrometer all the way to 200 micrometer. But as you vary this internal diameter, what happens is also that the volume that you contain the sample also changes. So you can see that, right, with the difference in the ID, short for internal diameter, the most commonly used ID is actually ID 50 micrometer. The reason is because, right, your volume in nanoliter will be about almost 2, and the total volume inside the capillary is about 981 nanoliter. So the consideration is really using the sample vial that I'll show you in class here, because if you have too much volume inside the waste, right, it'll be too much, and you need too many vials, right, in the auto sampler, which means there's less vial space for your other sample, for your buffer. So we need to mitigate this, the pros and cons here. Of course, it's always good to have more sample, but at the same time, more sample means you have more waste, and the total volume inside the diameter, the capillary will be increased. Okay? So, the most common sample injection method are the electrokinetic injection and the pressure injection. Now, with electrokinetic injection, right, one end of the capillary and its electrode are removed from the buffer compartment and is placed in a small cup containing the sample. Now voltage is then applied for measure time, by causing the sample to enter the capillary by a combination of ionic migration and electroosmosis flow. And then the capillary end and the electrodes are then returned to the regular buffer solution for the duration of the separation. Now this separation technique, right, discriminates by injecting larger amounts of the more mobile ions relative to the slower moving ions. And that's why there's a bias. In pressure injection, right, the sample introductions at the end of the capillary is also placed in a small cup. I just say it's a cup, but it could be a beaker, to a small vial. Now it contains the sample, but there's a pressure difference that drives the sample, right, by applying a vacuum to the detector, or by pressurizing the sample, or by elevating the sample, and we call it hydrodynamic injection. So the pressure injection does not discriminate because of ion mobility, but it cannot be used in gel-filled capillaries. For both the electrokinetic injection and the pressure injection, the volume injected is controlled by the duration of the injection. So injections of 5 to 50 nanoliter, and here it says 1 to 50, but 5 to 50 nanoliters are very common, and volumes below 100 picoliter have been reported. So for a buffer with a density and a viscosity near the values of water, right, a height differential of about 5 cm for 10 seconds hydrodynamically injects about 6 nanoliter with a 75 micrometer inside diameter capillary. So here we see that the other term for hydrodynamic injection is a hydrostatic injection. So gravity, pressure, suction. Alright, as we mentioned just now. Now I would like to introduce this B term here. If you look at this equation by the Hagen-Poiseuille law, that it just summarizes that, right? B, right, is this term, the rho g pi r power 4,
over 8 nu L.
This R is the radius of the capillary. Now the thing is, why we want to subsume it into a B term, because B is constant for the same system. Same system means you have same buffer, capillary, and all that, right? And if you make B the subject here, then you notice that the volume injected is proportional to the injection height and time. Now, next, we use this amount injected. Right now, we make W the subject here. The amount, you can tell me, what is the unit for W? Is it mole or something? Because C here stands for concentration. And if you have delta H that's in a single dimension, right? And this is time, right? And what is B? And then you calculate, what is the amount injected? Is it in mole or is it in grams, etc.? Take note that this delta H is the difference in height between the levels, because we are using the height differential to push it. Next part, let it continue. Take note this part is about B prime. B prime is slightly different. It's not the same as B just now, but what is consistent is that it's constant for the same system. In this case, we notice that the amount of the sample injected is proportional to the injection pressure and time, no longer about the height difference. Because now it's about pressure and vacuum, there's no difference in the height. Okay? So you just see that, right? We just want to group this term here, right? Pi R4 into B prime, that's all. Over the Ti over the 8 nu L. Next, we have to do a small corrections for capillary travel time between the reservoir, right? Or because this takes time to withdraw it to the other side. So this is the formula to look at what is the small correction involved. Normally it arises from some travel delay time because we need time for them to transport and siphon out, right, the capillary. Take note that the Wt is the amount of the sample injected during the travel time before and after injection. This is a schematic diagram. So when we insert some pressure in the sample vial, and you see that this vial here is encapsulated, because if it's open, right, then you can't force the pressure. If it's open system, then you can insert pressure, but then it won't be felt. So with this pressure, it forces the sample to go to the capillary and push it in. But there's a lag time because there's a reaction time. You're putting pressure to the air part, but then the liquid will fill it and get siphoned out through the capillary. Using vacuum is a bit better because it's more of a pull effect. So you look at the destination vial. Again, you're withdrawing a certain amount of air from the vial. There's a closed system, but because of a vacuum there's more propensity for the liquid to come up. Here the space and the replenishment come from the sample vial to compensate. In a hydrodynamic injection, gravity injection here, the difference in the pressure, if you recall in your previous pre-university days, right, how you have an inverted U-tube, not the video, but when there's a difference in the level, right, so there's a pressure difference and therefore there's a flow of the liquid from here to there. Okay? You can see the level of the meniscus moving. So the volume of the sample injected depends on the height, of the delta H, and the length of time of the vial is being raised. Now we think of the practicality of these three different kinds of injection, right? Hydrodynamic injection. If you are using difference in height, right, what happens is you need to have elevated platform here. You need to have a system that can allow, the delta H to shift. But how high can you get, right? And the more you shift, right, what happens is the capillary, it is flexible, but how much you want to play around with it? Does it make it more easily break or something like that? But for vacuum is hard to create a vacuum. You need maybe a lot of power. And how can you ensure it's a vacuum, right? You need to ensure that the system is really close, the vial cap is sealed. So think of the other consideration. Now, let's turn to electrokinetic injection, also called electromigration injection. So this electrokinetic injection is achieved by putting a voltage, right, like a Pikachu spark it, and then because of this, right, then those mobile ions will be inserted into the sample vial. This is the system, how it looks like. Right. How do you know that we are using electrokinetic injection? There's always a little rod. This rod is normally thicker than your capillary, and it's normally about silver color, right? So it's an electrode per se. And then when you put in some electrons there, it will just cause the flow of ions from the sample vial to the destination vial. And you notice that the detector is always closer to the detection vial. That's understandable because you need a longer pathway for the ions to run and separate. If you have a shorter runway, you can't tell the difference in the separation time. So here you have the length of the capillary, the sample zone, right? This L is the length of this L here is the length of the column, right? This length is the sample zone because when you inject the sample, right, it's a certain volume, right? So this is a zone. Remember, it's never like a line; it's a zone. And all the other terms we have explained before in the other lectures. So in terms of the amount of the sample injected, right, then it's a formula pi r square LC. You can see a bit more clearly perhaps, right? Pi r square is the area. When you have an area multiplied by a dimension, you have a volume, right? When you have a volume multiplied by the concentration, then you get, what do you have? You have mole, right? If the concentration here is in mole per dm cube. So we talk about sample injection, right? Because if the sample is too viscous, right, then it might be stuck. Lots of forces are trying to pull the sample out. On the other hand, right, the amount of sample induced by the electrokinetic injection depends on its migration velocity, right? And there's a bit of sample bias here because the voltage can cause those ions that's more mobile to move. Then those ions that's less mobile will be not likely to move, right? But if you use hydrodynamic injection, right, it's very fair because it's independent about this inherent ability of mobility due to the ions. So because of this sample bias, we call this effect some stacking. Though in the zone, there's a bit of a lag time between certain ions that's a bit faster at the front and a bit slower at the rear. But the stacking, right, we can use it to our advantage. We can use it to enhance the efficiency into pre-concentrate sample because now we are trying to put them together now. So it's like we are compressing the ions in a smaller volume. So that's a bit of like pre-concentration. And that makes sense because sometimes we are measuring minute volume, minute amount, right, in terms of ppb level. So we do not mind having some pre-concentration to lower the detection limit. Now, the amount of injection, the sample, right, depends on the injection time. So if you have maybe 2-second injection time, so it's like keep on injecting, right? And also the injection voltage for electrokinetic injection. If you spark a bit more, of course, you can excite the ions to move in a bit faster, so you have more sample injected. Maybe this diagram will illustrate a bit better. Recall that, right, your electrokinetic injection, the sample bias is, every time you spark it with the same voltage here, but the higher mobility of the ions, right, it goes in more, right? So it's never consistent. But if you're using a hydrodynamic injection, right, you're either using pressure, vacuum, or your difference in height, right, then it's always constant, okay, equal. So these are some equation to understand the bias factor, right, just to level it. Okay. Open book exam, you can refer to this to do some simple substitution. Now just note that, right, this bias term here, this factor is equal to 1 when the mu electroosmotic flow is large here, right? That means there's no bias there. Okay. Next, we all know that the sample bias comes in a difference in the conductivity between the sample solution and the operating buffer, right? Maybe we don't dissolve our sample inside the buffer, but sometimes we do because we want to keep this mobility closer. There's a less difference. But what if there's a huge difference here? Then how do we calculate, right? And this is the equation given. We talked about just now, right? What is W in the amount here? So evident now is mole because the concentration is in mole per ml. Okay. Here we see the different injection volume per second for this pressure of 0.5 psi vacuum or gravity, right, against the different capillary diameter. And we look at the most our favorite internal diameter, 50 micrometer. What's the pressure, vacuum, gravity equivalence here? And I would like you to look at this part here. If I have gravity 0.17, right, it is almost equivalent to half the internal diameter size for a vacuum. Okay, you see 0.17 corresponds to close to 0.19. Next, we had introduced something called the field amplified sample injection called the FASI. So a FASI, what's interesting is uses a plug, right? What is a plug in a separation science is you have a sample in a buffer dissolved in it with a lower ionic strength, right? So it's like a, you might say it's a band, it's a zone, right? To fix the zone. So how do you do that is you introduce either some water to contain it, so it doesn't separate out, so much. It's like a stopgap in a way. So what happens is, right, maybe it's easier for you to see a diagram there, right? That when you have a plug, right, which is this a ring fence area, it causes stacking, which means you pre-concentrate your sample here, although internally in this plug, you can have ions that move faster a bit closer to the front, the ions that's less mobile at the rear, right? But what it does is, it contains it in this region there. Now here, the y-axis is the electric field, right? This, remember your triangle, your peak area of a CE diagram. So what happens is you measure these ions, right? So okay, it comes down. Now, but with this delta E buffer, there's a bit of the buffer itself is ionic, so it has a bit of measurement. So the baseline is no longer flat, right? But it is it declines a bit, and therefore this fluctuation sometimes give you the noise, right? If you have a small delta E here, with a small difference in the electrical mobility of the buffer, right, then you have a slower migration. Okay, so I want you to look at it. This part is your sample plug, right? When here you have a concentrated effective sample plug. How do you do that, right? Sometimes we inject a bit of water, right? Why? Because the water has a low conductivity, it's like free of ions, right? So when you put in water, then within the plug here, right, then your ions will concentrate there.